Okay, so we're nearing the end of the functions in several variables section, but we first have to think about an important concept, and that is of Taylor series in more than one variable. Okay, so with Kathy you would have seen Maclaurin series. Okay, so if you have a function of a single variable, f of x, okay, you expanded that function, here's f of x, okay. You looked at Maclaurin and Taylor series, and the Maclaurin series is the expansion of the function around the origin, around x equals 0. Okay, and we saw some examples. Okay, so for example, if the function is e to the x, then the Maclaurin series for this is 1 plus x squared over 2 plus x cubed over 3 factorial. Okay, and 2 factorial is just 2, so we can write this as 2 factorial plus x to the n over n factorial. Okay, plus plus plus, and this can be written as the sum of x to the n over n factorial from n equals 0 to infinity. Okay, so this is the Maclaurin series for e to the x. We think about maybe cosine x. Okay, then this starts at 1. Okay, if x is 0, then cosine x is 1. Okay, and if x isn't 0, then we need other terms. So we've got plus, no, we have a minus in cosine. So 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial, etc. Okay, we can write this as the sum of x to the 2n divided by 2n factorial from n equals 0 to infinity. Okay, and let's just check. So if n equals 0, then we've got x to the 0, which is just 1, and 0 factorial is 1, so we get 1, that's our first term. If x equals 1, if n equals 1, so if n equals 1, then we've got x squared, yep, divided by 2 factorial, yep, okay, and so on. And sine x is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, and so on. Okay, we can write this as the sum of x to the power of 2n plus 1 over 2n plus 1 factorial, okay, from n equals 0 to infinity. Okay, so the 2n and the 2n plus 1 give us the even numbers and odd numbers, even powers and odd powers. Okay, so here we have even powers, and in sine x we have the odd powers. Okay, so this is the Maclaurin series, expansion of the function about x equals 0. We also looked at the Taylor series, Taylor expansion. And in the Taylor expansion, you expanded about not the origin, but some point x equals a. And you asked, what is the function at this value, which we'll call x, if we know the function at x equals a. So our Taylor expansion for our function was that f of x, so the function at x equals the function evaluated at a, okay, that's this value, plus the derivative of the function evaluated at a, okay, times x minus a, okay, the distance that you've moved away from the point a, okay, plus the second derivative of the function evaluated at a times x minus a squared over 2 factorial. Okay, up to the, and then the general term is the nth derivative evaluated at a, okay, divided by n factorial, and there's an x minus a to the power of n. Okay, so this is the Taylor series of a function about the point a. Okay, so you may know the value of the function at a and its derivatives. Okay, and you want to know what the function is some distance away from a, so x minus a here in this case. Okay, I think I've got the sound issue sorted, thankfully. Okay, so we're going to generalize this Taylor expansion. Okay, so this is the Taylor expansion for a single variable, function of a single variable, f of x, okay, drawn here. We're going to generalize this to be able to write an expansion for a function of 2 or more variables, okay? We'll focus on the 2 variable function as it's most instructive. Okay, so let me clean up the board and keep this in your mind. Okay, I'm going to write that again at the top once I clean this up. Okay, so keep this in your mind. Okay, so what we saw was that the Taylor expansion of the function, so our function f of x about some point x equals a, was given by the following: f of x equals f evaluated at that point a plus the derivative of f evaluated at that point a times x minus a plus the second derivative of the function at a, okay, times x minus a squared over 2 factorial plus, and then the general nth term was the nth derivative of the function evaluated at the point a, okay, multiplied by x minus a to the n over n factorial, and you keep going, okay? Okay, so what does this tell us? Okay, let's think about what happens when f prime of a equals 0. Okay, what does this tell us? And let's assume that x minus a modulus is small. Okay, so close to 0, much less than 1. In this case, our function, our expansion, becomes f of a plus, now we've said that f prime of a is 0, so the first derivative is 0, so this term is non-existent, this vanishes, plus the second derivative of the function evaluated at a times x minus a squared over 2 factorial. And we're going to ignore all higher order terms because we've said that x minus a is small. So the next term has some, okay, then we'll write down the next term, f prime prime prime, okay, third derivative evaluated at a, x minus a cubed over 3 factorial. Okay, but we're going to ignore these terms because we're going to say that x minus a is small. So a small number cubed is much less than a small number squared. Okay, so we're going to ignore these terms. Okay, we're going to stop at this approximation. Okay, and if we see what our function looks like, here's x, here's f of x. Okay, and here's the point A. Then we see that our function looks like a constant term, f of a, and then as we move so this value is fa. As we change x, okay, then this term comes into play. Okay, as we move from a, okay, to a point x, then x minus a becomes non-zero. And you see that it's x minus a squared. So this is a parabola. Okay, so in this approximation, when we have that the first derivative is 0, and we only move a small distance away, then we're always drawing a parabola. Here, this is called a stationary point. So f prime of a equals 0 is a stationary point. Okay, and if we've got two cases, one, we need to think about the second derivative. If f prime of a is greater than 0, okay, then that means as we increase x, our derivative is increasing. Okay, then we have a parabola like this, and then we have a minimum of our function. Okay, in the other case, if f prime prime of a is less than 0, okay, then we've got a parabola that's turned upside down, okay? Smiley face and sad face. So if it's less than 0, we've got the sad face, and this is a maximum. So the point f of a is a maximum of f. Okay, so what if the second derivative is 0? Okay. Okay, in this case, then we have to think about the third term. So in this case, we have that f of x is fa plus, and then this third term, which we previously ignored. Now this one's 0. So we've got the third derivative taken at a, divided by 3 factorial, which is 6. So we've got a 1 over 6. F third derivative, f prime prime prime, x minus a cubed. Okay, and then we get, again, two cases. I'll draw this graph again. So this is x, this is f of x, and there's a point a. So at x equals a, our function takes the value f of a. And here, the second derivative is 0, so this point corresponds to a point of inflection. Okay, so the derivative of the derivative is 0. Okay, so our curve may look like this. Okay, so you could think about y equals x cubed. Okay, if this is f, then f prime is 3x squared, f prime prime is 3x, and f prime 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 is 3. Okay, and at x equals 0, you have that f prime and f prime prime are both 0. Okay, but the f prime prime term survives. Okay, so you've got a point of inflection, and this point of inflection, this graph can be in one of two forms. You can have this, or you could have the other. The other being this type of thing, okay? So the curve turns over, the derivative turns over. All right, so you can have, yes, this will be f prime 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 of a less than 0, and this is the third derivative greater than 0. Okay? And the relevance is that we'll come back to After we look at Taylor series in two variables, we'll come back to look at stationary points of surfaces and find the maximum and minimum of a surface. And we'll see that with two or more variables, new considerations come into play. Okay, so this was the Taylor expansion for the function f of x about some point A. Okay, and we thought about another point x here, and rather than call this x, let's call this A plus h, where this h is the step size. Okay, so what we're saying is x, what we called x before, is now A plus h. Okay, so that means that our step size is x minus A. Okay, and if we write this in terms of these variables, then we've got f of A plus h equals f of A plus the derivative of the function evaluated at A times x minus A, which is h. Okay, plus x minus A squared, which is h squared, over 2 factorial f prime prime A, plus, and then we've got h to the power of n over n factorial f to the nth derivative evaluated at A. Okay, which is the sum from n equals 0 to infinity of f to the n, h to the n, h to the n over n factorial. Okay. Right, now let's introduce d, a differential operator, that is h, the step size, times d by dx. Okay, where it's understood that this acts on something. Okay, so this acts on something. Okay, so df is h df by dx. Okay, and in this variable d, we can write our Taylor expansion f of A plus h in a compact form. It's f of A plus d f plus d squared f, okay, over 2 factorial plus d cubed f over 3 factorial plus d n f over n factorial plus. Okay, so this equals the sum d to the n acting on f divided by n factorial, n equals 0 to infinity. Okay, so we've got this thing. Okay, and d is this operator, and it's understood that all the derivatives here are taken at the point x equals a. Okay, all derivatives at x equals a. Okay, and we can check that this d thing works. So df is just h df by dx, okay, which is just h f prime, and we evaluate it at a. Okay, so that's this term, and d squared f is hd by dx of hd by dx of f. Okay, and h is just a constant, so we can bring that out the front. It's h squared d by dx of df by dx, okay, which is just h squared, 2 differentials, and it's always evaluated at a, as we said. Okay, so this is the second term, etc. Okay, so we're going to use this, and it turns out that this expression is quite general, and it will tell us how we can write down an expansion for
a function of more than one variable, okay? In a very similar form to this. But we need to think about what changes, okay? And the thing that changes is the d, the differential operator, okay? All right.